Okay, so today I want to look at chapter 1.5, which is analyzing graphs. Now, these do not necessarily have to be graphs of functions. They can be graphs of any type. However, you should be able to gain an understanding of the type of a function that it is, or the nature of the function, just by looking at a graph. Today, let's first of all start with analyzing the various different aspects of our graph. First, realize that at any particular value, especially in the values that where you see things kind of cross on the grid, you realize that we can always give various different order pairs which represents these values. For example, this point here would be 5 and 7. And again, what that means in a function, we're going to designate this function, by the way. We'll just call it the generic f of x function. And essentially what it means is that if I have a function called f, if I input an x, I will yield an output as f of x. So therefore, if I input a 5, go through the function, I yield a 7 as a output, just for example. So every one of our points, I plug in a 4, I get a 0. I plug in a 2, I get a negative 8. I plug in a 1, I get a negative 9. I plug in a 0, I get a negative 8. Here I plug in a negative 2, I get a 0. Plug in a negative 3, I get a 3. I plugged in a 4 here, I get a 4. Plug in a negative 5, I get a 3. I plug in a negative 6, I get a 0. And I plug in a negative 7, sort of. We'll talk about that here in a minute. And I get a, let's see, that's a negative 5. Now, understand that that has a little circle there. So I actually, that means I've got a hole in the graph there. I can't include negative 7 in the graph, but if I could, it would yield a negative 5. So the first thing to notice about the graph itself is that there are an infinite number of points here, by the way, just because I picked the ones that are on easily defined by integer numbers on the grid itself. Then that makes it easier for a conversation here. So there is an infinite number of numbers to be had there. But for any x value, that always represents the input through the function, and then the other value, the y, traditionally, is the value outside, coming out of the function. So whatever this algebraic function is, it looks like it could be a part of the cubic function, x cubed type of a function, but that's beside the point. So what's interesting as well is that notice that I can always have multiple outputs that are the same. See, here at negative 6 I produce a 0, here at negative 2 I produce a 0, and here at 4 I produce a 0. That's absolutely functional. It's absolutely a function. Notice that for any given x value, I only produce one and only one output. So we are adhering to a function here. So when you go to consider the various different things we could ask about a graph, certainly one of the first and foremost things to ask is it a function? And in this case, we would say yes. Of course, you could probably draw a vertical line down through the graph anywhere along the graph, and you'll notice it only ever crosses one place along the graph. So certainly by the vertical line test, it is a function. By looking at the graph as well, we can come up with x and y intercepts. For x-intercepts, you would just basically show where it crosses the x-axis. So we have x and y-axis, or an f and an f of x-axis. Y is always f of x, right? F of x is the output of the function. So on the x-axis, we can see that it crosses in 3 different locations. Looks like at 4, 0. Let's do it this way. At 4, 0. At negative 2, 0, and at negative 6, 0. So there are 3 different x-intercepts. But notice that there's only one y-intercept. That point is at 0, negative 8. There can only be one y-intercept for a function, that is, because if there were more than one, there would be points over points, and it wouldn't pass the vertical line test. Domain and range, very important concept. The collection of all x values is the domain. So domain goes this way, and of course the range goes this way. More accurately, domain is the set of all inputs. By the way, these are inputs. So if there's an x value in a coordinate somewhere, then obviously it's part of the domain. As far as outputs, that's the range, then it's the set of all these y values traditionally in our points. So these represent all the parts of the range. Notice that a lot of times I refer to this as the ground level. So I can see that if it's below ground, it goes down to a -9. If it's above ground, it goes to a 7. So for the range, you can see that our y values, or our f of x's, are going from as low as -9 underground to as high as +7 above ground. Our domain, the collection of all x's, we can see it goes all the way from -7 all the way to +5. So that's the extent that x goes. However, we need to be real careful here because you'll notice I do have a hole there. I can't include -7, so I am going to use an interval for an inequality as my interval, and I'm going to not show an equal sign there because I can't include it. But on this side, certainly I would include the 5 because there is no hole there. It's actually a solid dot. So, and I did mention to you that notice you include the -9 and 7 for the range as well. So I do it that way. Remember that we could alternatively give these as interval notation. I could go from, let me make that a parenthesis right there. I could go from -7 on the left-hand side to a +5 on the right-hand side. The bracket means to include the 5. The parenthesis means to not include the -7. But those are the borders, left and right. And of course, we're going to use a pair of brackets here because we include on both the left-hand side and the right-hand side. So what does it mean to look at the graph and say, all right, let's evaluate for various different points on the graph? What does it mean to ask, where does f of x equal 0? In other words, if f of x represents our set of outputs, or a potential output, if f of x traditionally can be replaced with a y for our own, to benefit our understanding, then aren't we saying, where does the output of the function equal 0? Where are the outputs equal to 0? We can see the outputs are equal to 0 in these three places. It's right there where the y values are 0. In other words, if the x-axis is called y equals 0 as an equation, then anywhere that it crosses would be where the outputs are 0. So when we ask where does f of x equal 0, what we're actually asking is what are the x-intercepts? Where does those occur? Because x-intercepts occur where the output is 0. So, and if it says list the values, I'm just going to list the values of x. That occurs when x is equal to 6. It occurs when x is equal to -2, and it occurs when x is equal to 4. Where do you think we would be able to say, where are the outputs less than 0? Where are the outputs less than 0? Of course, as we said, if we're talking about y values less than 0, then we're talking about everything underground, aren't we? Everything underground. If we wanted to know where f of x's are greater than 0, then we'd be talking about everything above ground. So if that's the case, then we just need to figure out what those intervals are. So where are these located? If these are below the ground, what are the intervals we are talking about here? Doesn't it occur in this area of the graph? We're responding in terms of x, aren't we? We want to always give intervals in terms of x. So when x is in this area, right, that's where it's occurring. And also x is occurring when x is in between this area from -2 to 4. Because these are the x values at the same time that the y values are less than 0. So if I were to express what my intervals are here, I would express my intervals, well, they occur when x is between -7 and -6, only I have to, and notice here, I can't, actually I made a mistake. You cannot include the negative 7 in the 6 itself, because we're not including the 7 here, and at negative 6, it is actually, the function is equal to 0. It's not less than 0. So we can't include that point. And we have another section of the graph where x has to be between 2, negative 2, and positive 4. And notice once again, we can't include the negative 2 and 4 because the output is 0 at that point, not less than 0. So those are our intervals for that. I just left them as, I didn't write interval notation, so to do interval notation, I would just use all parentheses, 7 and 6, and negative 2 and 4. Those are our intervals. Now, where does it happen when f of x is greater than 0? Certainly, we just look and see the values of x where that occurs. It occurs here for values of x, and it occurs here for values of x. And I'll let you, for the sake of time, I'll let you write those intervals yourself. What does it mean to evaluate a function for f of 2? Well, doesn't it mean that we plug in 2 into the function and see what the output is? So all we have to do is look along the graph to see where x is 2, which happens here, and then go down and see what the output is for an input of 2. If the input is 2, what's the output? In this case, the value is negative 8. Don't need algebra to plug in a 2. All we have to do is look at it on the graph. If we want to know what the output is when the input is negative 5, we just go to x values at negative 5 and we see and go up 3, and we can see that it outputs a 3. How about looking at where does f of x equal 4? What does that mean to do? Well, that simply means to look and see where 4 is a point on our graph. And of course that happens in a couple of places. It happens here and here. So there are a couple of different values. X in this case would be both negative 4 and positive 4.5. That would be for this problem. And of course, to look and see where it's negative 5, all you would have to do is see where we have negative 5 for our outputs, our y values, and then just go negative 1 for one x and 3 for the other, it looks like. Can't include this one because it has a hole in the graph. You should be able to evaluate functions and then subtract the two together. You should be able to multiply a number to a function once it is evaluated. This means to find the function for f of 1, which of course happens at negative 8 there, and then multiply by the 3. So if this is negative 8 on its own, negative 9, 1 and negative 9. And if then we multiply it by a 3, we get a negative 27, don't we? Now, the last thing I would be interested in showing you is what absolute minimum maximum values of the graph are. Absolute means overall. So for the overall min maxes of the graph, we are looking at the highest output and the lowest output. That is our maximum overall absolute value. Another way of saying that is, what's the high point of the range? What's the low point of the range? This is our absolute max. This is our absolute min. How high above ground do you go? How low below ground do you go? So this is really easy. We can state this in terms of y. Y goes up to 7 as a max. Y goes down to negative 9 as a max. Now, as for relative maximum, another word for relative is just local, meaning in your neighborhood. If you lived at the top of the hill, you would be the maximum place on the top of the hill. Here you see a hill. It's not the overall maximum of the function, but it's certainly the localized or relative maximum. Notice that y goes up to 4 on that maximum here. So we do have a local maximum at positive 4. We also have a relative or local minimum down here as well. So this overall minimum is also a relative minimum. So it gets us down to, in this case, a negative 9. So there is a local minimum at negative 9. What's interesting about local minimums is that they're at the bottom and tops of hills. Notice that when we do this, the function actually changes direction. When we talk about relative mins and maxes, it comes with a change of direction, and that's very important because the direction change denotes that our values of our function, our outputs, start to change their trend from perhaps going up at first, going down, and then going up again. For example, as x travels from the left to the right, gets bigger. Notice how as x is going this way, notice how the function outputs are increasing until it gets to that point. And then it goes down again, and then it starts to rise again. So we have an increasing section of the graph, which can be seen in this area and in this area. So there are two different areas of the graph you can see. And then a decreasing area of the graph here in between the maxes, the max and the min. So let's redo that yellow, which didn't look very good. So I'll use maybe a darker green. So these green areas are areas of increase, and then the purple, and then the pink is the area of decrease. And you should be able to express these as intervals. So remember, intervals are written in terms of x. So x is between -7 and -4 here. X is between 1 and 5 here. So those are the two increasing intervals. And then between -4 and +1 values of x, you have a decreasing interval. So on this worksheet, we're not worried about numbers 1 and 23. We'll talk about those at some other time. This is just an arbitrary question to ask. Can you actually draw a horizontal line in order to see where the graph goes through that line? Certainly, I would hope that you could do so. This is all you need to know in Chapter 1.5, Analyzing Graphs. Be able to analyze a graph completely and entirely. Be able to identify areas of increasing and decreasing on a graph. Be able to show me mins and maxes, both absolute and relative. And be able to tell me the outputs of functions for given inputs and vice versa. And that includes intercepts. Functions, obviously be able to tell if it's a function, obviously be able to tell me the collection of all domain inputs and the collection of all range outputs. Very important to be able to do everything that you see on this simple but messy assignment. Thanks for paying attention. Bye-bye.